Hello everyone, we'd like to introduce the autofocusing and color identifying lenses for mild visual impairments, also known as P.A.U.L. Our team consists of Kayla Stanley, a computer engineer, Julie Gallagher, an electrical engineer, Renato Morales Jr., a photonic science engineer, and Midhat Satanov, a photonic science engineer.
Around the world, billions of people suffer from some form of visual impairment. In the United States alone, the optical industry is valued at over $68 billion. However, across the globe, many are not having their visual needs met. The expensive price of eye lenses and the abundance of color blindness, with 1 in 8 men having some form of it, means that there are untreated and overlapping issues affecting billions.
This is where the autofocusing and color identifying lenses for mild visual impairments, or P.A.U.L, comes in. P.A.U.L assists the user by identifying colors in their environment and sporting a series of lenses that can be manually or automatically adjusted to the user's specifications. The system is button-based, allowing the user to quickly cycle through P.A.U.L's features while receiving audio fit confirmation by connecting a personal Bluetooth audio device. This is our main PCB. Here is the ESP32, a 3.3 regulator in the middle, and a 5-volt regulator. Here are some of our connections. So the connections to the TCS 32000 is over here. We also have some connections for our buttons, and connections for 3 motors are on this side of the PCB, and on this side we have the ultrasonic sensor connection.
You can see our buttons right here on the side. We have our reset motor button, and on the side of the head we have our 4 buttons which control backward movement for manual focus, forward movement, our autofocusing system, and our color identification system. Here is our Raspberry Pi. You can see here, these are the attachments to the ESP32 for our serial connection. This is the connector we have to our Raspberry Pi camera module, which goes right here on the side of the face.
This right here is our colorimeter. It's designed with a case in mind that houses LEDs and the photodiodes within, and we can see that a lens is in front of them in order to focus the light better.
Here we have the ultrasonic sensor. This takes the initial distance that we use to determine how much the primary lenses need to move in order to acquire focus for our autofocusing system. For our system, we are utilizing 3 motors. There's 1 on the right and there's 2 on the left. These motors are used to adjust the distance between our lenses. As we adjust the distance between the lenses, we can adjust the focal length and also the optical power of the lens system itself. First, this system is adjusted into focus, and once this focus is acquired, it adjusts the focus of the primary lens system in front of the user's eyes. This allows for autofocusing to be achieved. For our lenses, we are utilizing negative lenses in addition with positive lenses in order to achieve the negative optical power and the positive optical power. When separated by 50 millimeters, it has 0 optical power. As we bring the lenses closer, the optical power is reduced into the negatives. As the lenses are separated, the optical power is increased into the positive. For our system, we will be achieving negative 1.5 diopters and positive 2.5 diopters.
This is our battery pack. One of the batteries connected to the ESP32 right here, and the second one is connected to the Raspberry Pi. It's attached to the arm of the user.
With that out of the way, we do want to state that that will not be P.A.U.L's final appearance. In its final iteration, a lot of that wiring will be cleaned up, so please do come by our booth so you can take a look at him. Now, we would like to go ahead and go into several different subsystems and show off P.A.U.L's features one by one. So right now, we're using the autofocusing feature of our system. We enable the system by pressing that button on the side, right there. Then, the rails on the left part of P.A.U.L move in correspondence to a picture taken by the CMOS camera. The CMOS determines whether or not the image produced is in focus or not, and then, using the distance measured by the time of flight sensor, moves the rails back and forth until the image is considered in focus. It then moves the secondary lenses in front of the user by that same distance in order to bring their vision into focus. This is the color detection portion of our project. It incorporates the colorimeter and then also the CMOS camera, taking inputs from both and then comparing them to determine the color of the objects that the user is staring at. So in this case, we have a blue box, and we're going to go ahead and use the system on it by pressing the button.
Identification has started. Blue.
And we can see that it detects blue. Now as for red, we'll try that now.
Identification has started. Red.
Now for green.
Identification has started. Green.
Right? And now we can see that our current design only incorporates red, green, and blue primary colors. However, we do hope that by the time of the live demo, we might be able to incorporate secondary colors as well.
Now we are testing the manual focus settings. For this one, we will be using the CMOS, since you will not be able to see what I can see. So we'll be using the CMOS to represent the adjustment of the focus. Currently, the separation between the lenses is 50 millimeters, which corresponds to 0 diopters. If we press a button, we can change the optical power by increasing the distance between these lenses. We can change the optical power by half a diopter at a time, whether it's positive or negative. If we want to increase the optical power, we have to separate them
0.5D.
5 millimeters at a time. If we want to decrease the optical power, we have to reduce the distance between them 5 millimeters at a time. Now to test the maximum optical power that we can achieve, or at least a large value, we've placed the system in front of a poster 286 millimeters away. To achieve focus here, we are going to require 3.5 diopters and a separation of 85 millimeters between the lenses. Let's achieve that optical power now.
Here we can see the resulting image after we've used the manual focus, and you can see looking through the lens that the system is clearly in focus.
Thank you for watching our video. Team P.A.U.L appreciates your attention.